Okay, so we'll try to just go in order here. Um, so sinusoid is just the name for a graph that looks something like y equals sine of x. That's where the sinusoid part comes from. So it's the name for any of these graphs that looks like that, right?
Mhm.
Um, Part of the reason we learn these is just a lot of things in the world go this way. Tides are a good example. If you wanted to graph high and low tides, that's what it would be like, and plenty of other examples of that.
Mhm.
Um, Definitions, we'll come across those definitions as we actually graph them. So we'll make sure at the end that we've done all those. Um, just in general, do you feel comfortable with function notation? Forget about trig stuff for a minute, but if we just have like that and ask you to do like all these things.
Yeah, I guess so. Yeah.
So those are all clear, like what's going on there.
Mhm.
Um, so let's look at the different like transformations, I guess, that they've listed here. So we've got, so if we just have some regular functions, we've got f of kx, f of x plus k, f of x plus k, negative f of x and f of x. Okay, actually a bunch of these. All right. I'm also going to put over here sort of it's a pretty good general rule, actually.
Mhm.
Um, it looks a little weird, but ends up being a pretty good general rule. Um, yeah, let's start the other way. And we'll see, in a minute, kind of what this actually means. But this is a pretty good general guideline. And I'll give you an example just from something that you already know. So
Mhm.
have like, oops, if we have uh, y equals 3. So like if we have that and we want to compare it to just the regular graph of y equals x squared,
Mhm.
okay, this is outside the parentheses. It looks like it would make things 3 times bigger, and it does. And it affects y times. So it's 3 times as tall, right? This is outside the parentheses, so it affects y. It looks like everything would move up 1, and it does. It moves everything up 1. This is inside the parentheses, so it affects x. -2 makes us think it would go 2 to the left, but it actually, as we know, goes 2 to the right. Yeah.
Mhm.
So that's sort of what I mean about it affects x opposite of how it looks. One thing that I didn't put in there, I guess, is if we had like, say we had that. So now we're inside the parentheses, so it affects x. This looks like it would make x 3 times bigger. So, instead of that, it looks like it would make it like that, right?
Mhm.
But inside the parentheses, opposite, this big number actually makes it narrower.
Okay.
So that's what I mean about these two things, and we'll see how that plays out with these. So let me get rid of those last two. Um, so here's our starting point, f of x. this one here, kf of x, it's kind of like this, right? We're multiplying. By the way, f of x and y, same thing, right? So this looks like we're multiplying y by something, and we are. Y is multiplied by k. So how do we want to say that? So I guess vertical stretch is really what we should say. And again, the way that it looks, if k is a big number, then it gets stretched higher. The second one is, that's this scenario. It's inside the parentheses, so it affects x not the way that it looks. So this is but narrower one. So that kind of fits with what we've said, right? This one is also kind of like what we looked at here. And so this one we know, like pretty much any time in math that you've seen, like let's say you factor something. We know what we do with these things. We set them equal to 0, right? Same thing here. Whatever's in there, set it equal to 0 to find horizontal shift. And as we saw, like if it's a minus, it'll actually go right. If it's a plus, it'll actually go left. This one we saw in this example as well. This is just vertical shift, the way that it looks. There we go. Okay. Negative f of x, so that means that you're taking the y value and making it negative. So this is flip across x axis. And just to be 100% clear here, like, oops, if, so a vertical flip means you're going across the x axis, but the y values are changing, right? Does that make sense? So if we're going from here to there, like all the y's are going from positive to negative. What we're actually flipping it across is the x-axis. And then likewise, this is flip across y-axis. So those are all the various transformations that can happen, basically. And Linda. Is that, I mean, we'll obviously have some examples, but is that reasonably clear how those work?
Wait.
Which one are you looking at?
I'm looking at the fx plus k one. So the first one, the f in parentheses x plus k is
Yeah. So
also like minus.
Yeah, let's do a couple quick examples with this. So it's these two that you're looking at.
Yeah.
So
yeah.
We have okay. So we have let me just write down what these are. X plus k, and then f x plus so let's just say our, f of x equals x squared. We'll just do a simple one, and k equals 3.
Mm-hmm.
So um, so that first, actually, you know what? I'm just going to make this a little bit more clear here in a second. So we'll do f of x. So I'm just going to put the parabola there. And then let me switch colors. So this one, that's a vertical shift the way that it looks. So if k is 3, then we're just going up 3. So that would be wherever we think 3 is. If we have, so that's inside parentheses, so it's a horizontal shift the way that it looks. We can also just think of it as, so that's a shift of -3. So that would be like that.
Uh-huh.
Right, so the outside the parentheses is vertical the way that it looks, so +3 means it goes up 3. Inside the parentheses is horizontal, opposite of how it looks. So +3 actually means 3 to the left, not 3 to the right.
Okay. So
Just in general, if somebody says like, you know, what's the difference between f of x and f and, you know, here, let's do a couple of these. -2 f of x minus 1. You'd say that the second one would be, so that's -1 inside the parentheses, so horizontal, but actually to the right. And 2 means it's vertical stretch by factor of 2, so double. And then across x-axis. And I think we'll probably have some more practice questions with this, but you kind of see where that's going.
Mhm.
Let me see what's the next thing written on here. Yeah, so you know, one thing we could say here is if we had an original point that was like 3, 7, that came from that.
Uh-huh.
Okay, so that means this new graph is shifted to the right by 1. So now 3, 7 becomes 4, 7. Vertical stretch by a factor of 2. So now 4, 7 becomes 4, 14. And flipped across the x-axis, so now 4, 14 becomes 4, -14. So the original point 3, 7 on this first graph, like that same corresponding point is now located at 4, -14 on our new graph. When we get through this, we can do, actually, let's do it now. Let me save these and we'll just go to Desmos and do a couple of examples so you can kind of see them all at once. Okay. Welcome back.
I think it cut out.
Yeah, that's fine. I was just saying let's actually do a little bit on Desmos now so you can kind of see this
Okay.
shared. So let's say again we just have y equals x squared. Okay. We'll kind of change one thing at a time here. And Desmond is great for just like playing with this and figuring it out. So let's say we put in y equals, let's do x minus 1 squared. You can see that that has shifted our graph as we would expect. This is x minus 1, so 1 unit to the right. Yeah? Let's add 3 at the end. So that should take our original, well, not our original, our green graph, sorry, our blue graph, and move it up by 3. Anyway, so we've gone from original graph in red, 1 to the right, and now 3 up.
Okay.
Let's do, let's put a 1/2 in front of that. So that should be vertical stretch by 1/2. In other words, it's actually kind of a vertical shrink, right? The graph should look a little shorter and fatter when we do that. And it does. So now it's, and I'm going to do the first couple here. So now we've made it a little bit shorter and fatter. And then one more thing we could do is, let's do a vertical flip. So now it should go from there. And now it's the same thing reflected on the other side.
Okay.
Yeah.
Yeah, I think I get that.
One that's a little, that can be a little tricky. Let me go back to, I'll kind of go back to one of the original ones. So got y equals x squared. Let's do, that's a good number that's going to work here. And let's do, okay. So you notice how these two that I just did came out the same.
Yeah.
And you can tell algebraically, if you multiply this out, it obviously comes out to the same thing as this one. So here's the idea. This one, there's a coefficient in front. So we said that's a vertical, in this case, a vertical like shrink, because it's less than 1. And so the way you look at this, and you can see my mouse on here, right? The way you look at this one is, okay, where there used to be, let's say, a point at 2, 4. Oops, I did that wrong. 2, 4. There we go. Now there's a point that's a quarter that high. So there's a point at 2,
1. Yeah.
You can see everything's moving down, right? If we look at this version, okay, so this one is saying that, remember we said inside the parentheses means it affects x opposite how it looks. So this affects x, but since it's a small number, it actually gets wider. Okay. So that same 0.24, if we're looking at this version, we'd say, oh, the graph gets wider. So now that same 2,4 becomes, what's going on here? What the heck? Becomes 4,4. And so we're sort of looking at it a different way. No, what am I doing here? 2, 1. So we're looking at how the graph changes sort of in a different way. This one, we're saying it shrinks downwards from that point to that point. This one, we're saying it widens from that point to that point. Now, it produces the same graph, right? Like we saw that these are just the same graph overlapping. Where it does make a difference is on your worksheet where it says the last thing in B, where it says find the point on a transformed graph corresponding to the given point on the parent graph. You see that part? It's the last thing in B. Did you freeze? Oh, you may have frozen. I will wait for you to come back. Baby bear, hi. Baby the bear.
My bad. It
Okay.
keeps the Wi-Fi keeps me.
I figured usually I'm like, okay, if he's really staring at something for more than about 5 seconds, he's probably frozen. So
Yeah.
So I don't know what the last thing was that you heard, but on that sheet that you sent me, do you see the last thing under B?
Wait, the last thing under B.
It says find the point on a transform graph corresponding to the given point on a parent graph.
Give alternate graph. Oh yeah, 2B, yeah.
So, as we were saying a minute ago, like, yeah, these two graphs, they come out the same, whether you write the quarter in front or the half in the middle.
Uh-huh.
Corresponding points are not at all the same, because if you look at one of them, if you look just at the y equals 1/4 x squared, then that point and that point correspond. If you look at the 1/2 x squared, that point and that point correspond. So it ends up actually being very different, even though the graph is ultimately the same.
Okay.
So you blink, so I know you're not frozen.
Yeah.
Okay. Cool. Let's go. So that's all in the recording too. Let's go back to and we can talk, I think, more specifically now about let's see, graphing transformations. So let's do a couple of these. Okay, there we are. Let's do a couple of these, sort of going backwards from graph to starting point. So we'll do this in Desmos. Let me go back there. Let me get rid of all those. Should we do this with? Let's do this. Let's do. And on these, like, I'm going to show you what I'm putting in, but we're still going to go through the process of how you would like backtrack and figure it out. So let's do. Let's do 1/4. So let's say that we had, and I'll give you a couple of points here. So we have that as a point corresponding to 0, 0. And then maybe we have, so instead of 1, 1, we now have 6, -1.5, -1.75. Okay. So let's say we had what would we have here? Let's have just that graph, and let's say we know it's y equals x cubed. Just because we know the shape or whatever. Or the question says, what's the transformation from y equals x cubed? So, and we know that that's kind of the middle point. So we could start out with sort of the easy part. It's some version of y equals x cubed.
Mm-hmm.
We know that it's 5 to the right, which means x, but it's x minus 5. Oops. Okay. We know that that's down 2. It's at negative 2. We know that to get down by 2, it's just minus 2. So we've got everything except our vertical stretch or compress. One way we could do that is we could basically write, so we know the equation is of this, sorry, I put to the 5th power. That's obviously not what I meant. That same idea. We know that our equation is of that form, right?
Yeah.
And so we could put in this point that we have. We could put in negative 1.75 for y and 6 for x, and then just solve. Of course, this is Desmos, so we can also use a slider. And this is actually another great tool. You notice how let me get this out of the way just so you can see. The bigger a gets, the faster, the steeper it is, basically, right?
Mm-hmm.
As a gets below 1, it's shallow, and then notice as a gets below 0, then it flips. But we can tell, if this is a equals 1 here, we're obviously going for a pretty small number. You can see it's somewhere between 0.2 and 0.3.
Yeah.
So if we just plugged in those points algebraically, we'd get a equals 0.25 or 1/4. Oops, what am I doing? Yeah. Let me see if that seems to, let me make sure I haven't missed anything so far. Yeah, okay, so let's say we have, let me put the actual one back in there. Okay, so we've got original graph and then transform graph. And question says, let me get rid of some of these points here. Question says, the original graph had a point, it's a good one here, -2, comma, -8, hopefully. Yes. And we want to find the point on the blue graph that corresponds to that point on the original graph.
Mm-hmm.
So first thing we'd look at is there's no horizontal stretching or compressing. Right? Actually, let's throw that in. Let's do that. Okay. So yeah, so now we've got a little of everything. We've got vertical and horizontal stretch. We've got vertical and horizontal shift. So we've got everything in there.
Mm-hmm.
Okay. So we want to find the corresponding version of that point on this graph. Okay. So yeah, I think it was, I definitely just made it harder. So that -2 Well, here, let's just write what we have. So now the horizontal is so now the horizontal shift, because we set that equal to 0, horizontal shift is 2.5 to the right.
Mm-hmm.
Vertical shift is -2. Not vertical shift. Vertical shift is -2. Vertical stretch 1/4. Let me write this in another box. So again, this makes it look like it's wider, but it's actually narrower. Horizontal, we'll call it compress by 1/2. Okay. So this is the part that's tripping me up slightly. So if, oh, hang on, I need to plug in. Give me 1 second just to make sure I'm doing this right. Pretty certain.
Okay.
Make extra sure. Okay. +5 is 3, x equals 1.5. That should work, right? Yeah, okay. All right, so here's how we would do this. So we need the spot where the corresponding point would be where this equals -2.
Mm-hmm.
Okay, so we set 2x minus 5 equals -2. That ends up being x equals 1.5. And just to show you if, well, we'll get there. Okay. And then when x equals 1.5, so we can just plug that in, right? There's something about this that's tripping me up, as you can tell, and it has to do with this. Other than that, everything is totally normal. So let's see, when x equals 1.5, then that's -2, that's -8. I'm kind of doing this to myself real quick. That's -8, that's -2, that's -4. So let me see if this point makes sense. Okay. Yes. Okay. Yeah. So I guess our directions for this would be, if you want the point that corresponds to that, set that equal to the x value, and then find what that gives you for the y value. So what I did was, the corresponding point would be where this equals -2.
Mm-hmm.
And then the corresponding y value would correspond to -8.
Okay.
So that equal to -2, we got x equals 1.5. When we put 1.5 in there, the output of this is -4. Now, we can see, so I'm going to go back and put in 0, 0, and that point or the middle point here. So I'm going to put in those for reference. So let's see what's gone on here compared to kind of the middle point of the graph.
Mhm.
This graph, the starting point should be 2.5 to the right and 2 down. It is. Okay, we've got that. This change here, because it's 2x instead of just x, that change should happen in half of the amount of space, right? We
Mhm.
said where it looks like it's twice as wide, it's actually half as wide. So here, that took from 0 to -2. So that took 2 units to change that much. Here it takes, oops, no, I can't do that. Here it takes 1 unit to change that much, from 2.5 to 1.5. So it is indeed changing twice as quickly if we look at the horizontal. From here, that particular change, y changed by 8, right?
Mhm.
But this is a quarter as a vertical compression. So instead of 8, it should only change by 2. So this goes from -2 to -4.
Okay.
So a little, you can see how, you know, this and this affect the starting point, and then like this and this sort of affect the rate of change. Linda, what did you just find? Hang on a second. Linda, what are you doing up? I don't know what that is. That's not. Thanks, Linda. Good job. Taking us. Yeah. So again, general idea, set that equal to the original x,
Mhm.
find what x is, and then figure out what that tells you y should be. I know that wasn't totally smooth. I might later on kind of redo a couple more and send you some more polished videos. That one, again, it's easy other than that part. That part just kind of,
Yeah, it's kind of complicated. Or
make
it's
sure
weird.
other things. So that was kind of 2C. All right, graphing sinusoid. So let's go to how the formula for the argument determines the phase shift and the rate at which the terminal ray rotates. At the rate at which the terminal ray rotates. Uh, let's go to graphing, because that one, I might have to look up what they mean by the terminal ray rotating. Let's just do kind of the basics of graphing. Again, do you have any practice questions with this, or do you just kind of have this sheet?
I just had the sheet.
That's fine. Yeah, okay. So let's do the graphing thing.
Okay.
This one I will go through pretty quickly. Again, you'll have the video and the notes and all that. So, okay. So the first thing to know with these, and by the way, I don't know if you're doing these in radians or degrees. Do you?
I think it's. I'm gonna check.
Yeah.
Um,
Not that different anyway, but
I think it's radians.
okay. So first basic thing to know is that sine curves start at 0, go like that. And so this would be the end of one period right there. Cosines start at 1 So that would be the end of one period right there.
Mhm.
We can extend it. So there's the end of the second period for sine. There's the end of the second period for cosine. For both of those, the period is 2 pi, or I'll just put, if you're doing it in degrees, it's 360. So when we graph one of these, so I'll just do a couple of examples here. Say we're graphing y equals 3 sine of, well, there's a couple of very slightly different ways that these could be written out. But let me actually see exactly what. Okay. Minus 3 plus 1. So we kind of, we'll put the whole shebang into this one. The things that we need to find are vertical shift, horizontal shift, amplitude, whether there's a flip, a vertical or horizontal flip, period, and then if we're graphing segment, which I'll explain that in a second.
Mhm.
We know how to find vertical shift, that's just that. We know horizontal shift means setting that whole thing equal to 0.
Mhm.
So that's going to be 2 is pi over 3, so it's pi over 6. Amplitude is just 3, that number's right there. Flip, no, there's no negative there, there's no negative there, so there's no flips to worry about. There's a formula for period that's really simple and really important to know. Period equals 2 pi over b. This number is b, whatever front of the x or theta. So in this case, period equals 2 pi over 2, so pi. Remember we said a couple times that like this number, so this affects x, it makes it look like x will be bigger, but actually this makes it narrower, right?
Mm-hmm.
And so it makes sense. The period is only half of what it usually is, so the whole graph is narrower, it kind of shrinks inwards. Okay, for graphing purposes, we're going to say segment here. What I mean by segment is period over 4. And I'll show you why that's useful in a minute. So here, what I'm going to put for segment is pi over 4. Okay. I'm going to end up wishing that I wrote this on the page. I'm going to, can I just delete these and so I can graph up here without having to do it on a new page?
Yeah.
Because otherwise we'll do a lot of back and forth. All right. So, okay. Okay, so here's how we do the actual process of graphing. All right, for my horizontal axis, so I have a shift of pi over 6, and every period is going to be pi. So that gives me a sense of how, how I need to label my axis. So I'm gonna say that's pi over 6. That means that my first period is going to be done pi units later, so it's going to be 7 pi over 6, right?
Mm-hmm.
So my one period that I'm going to graph is going to fit in there. When we graph sines and cosines, what's going on? When we graph sines and cosines, you can see how like any cycle is kind of split up into 4 pieces. There's like the up part, the down part to there, the down part to there, and then the up part back to there. Okay.
Mm-hmm.
So that's what this segment thing's about. So that first up is going to take pi over 4 to happen. Right, here's where these can get a little bit maybe a little annoying. So let me split this into 4. Okay, so like this spot is going to be pi over 6 plus pi over 4, right?
Mm-hmm.
Which is, of course, as we all know, so that'd be 2 pi over 12 plus 3 pi over 12 is 5 pi over 12. This spot is halfway between pi over 6 and 7 pi over 6. So that's 4 pi over 6, which is 2 pi over 3. This is 2 pi over 3 plus pi over 4. So 8 pi over 12 plus 3 pi over 12 equals 11 pi over 12. Okay. So now we've got the horizontal part all labeled. We've got the beginning and end of our first cycle, and then each of those 4 segments so we know what's going to happen to the graph. There's a vertical shift of +1, so let's work on the vertical part now.
Mm-hmm.
Oopsies, that's not. I'm just going to sort of arbitrarily call that 1 right there. And I'm going to put in, actually I'll do this in a second. Since the amplitude is 3, we know that the graph is going to go up as high as +4. So that's also going to go 3 down to -2. I'm going to put in here, to make our graphing a little easier, I'm going to put in a midline right there. And I'm going to put in lines at the top, the highest the graph will go, and at -2, lowest the graph will go.
Okay.
So you notice what we've got now. We sort of said, forget about the X and Y, like the regular axis. We've now labeled the parts that actually matter to our graph.
Mm-hmm.
So we have the period, the horizontal shift, all that accounted for. We have the vertical shift and the amplitude all accounted for. Now we just need to put in some points. So this is a sine graph, so it starts at 0, but in this case, horizontal shift and vertical shift. Oops, let me change colors. So it starts right there. That's our 0, right?
Yeah.
First thing sine does is it goes up. So at the end of the first segment, it's up top. End of the next segment, it's back down in the middle. And again, our middle, not the real middle, but our middle. End of the third segment, it's at the bottom. End of the fourth segment, it's back to the middle. And so close enough. Good. So every segment either goes midline to amplitude or amplitude to midline. And that would be a graph of 1 period. And obviously, the directions might say to graph 2 or 3 periods, in which case you just do that again.
Mm-hmm.
But that's the general version of it. Let me see if yeah, okay. So let's do one. I want to do this. Let's do one where it's not a graph and we're trying to work backwards. So let me see if I can do a good one of those. So let's do okay, so we've got that. Let's do so that and then we'll do a good job of drawing this. So let's do that. Try to do an accurate drawing here, make it a little easier. Am I doing that right? No, my scale's super messed up, so hang on a second. Yeah, let me unmess up my scale here. Hmm. Okay. All right, that's better. And then we'll go there, 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 there. Okay. So that's the graph a little bit.
Mhm.
It's fine. So we're trying to backtrack and find the equation. Any of these sinusoidal graphs, so there's actually going to be many answers.
Mhm.
In particular, there's always going to be a sine answer, and there's always going to be a cosine answer.
Okay.
I'll show you how you can get that. There's also, let's say you notice like that point and that point are the same, right? Like
Mhm.
start of a cycle. So even within one of these, we'll get different answers if we say that's the horizontal shift versus that's the horizontal shift.
Mhm.
They'll both be right because they're both the start of a cycle. They'll just be answers. So there's many possible answers for these. Let's start out and say we want to do a cosine one. Remember, cosine normally starts high, goes low, and then comes back high, right? This graph
Mhm.
starts low. So that's an indication that this is going to be a negative cosine. If it started high, that would be a regular cosine. This is going to be a negative cosine because it starts at the bottom and then goes up.
Okay.
The next thing we can figure out easily is the amplitude. So from the midline to either the top or the bottom is a distance of 2, right?
Mhm.
Okay. So we know where the amplitude goes. That goes there. It's like a vertical stretch. Amplitude and vertical stretch are the same thing. If we're using this as our starting point, then sort of backtrack here. We'll say x equals negative pi. So x plus pi equals 0. And that's what we would put in to get our, sorry, I need to do something before that. Just kidding.
Okay.
The period is 4 pi, right? From negative pi.
Mhm.
Period equals 4 pi. We know that period equals 2 pi over b. So 4 pi equals 2 pi over b. B is going to be 1/2. So we know that's going to be 1/2 x. Now we can go back and do this other part I was just doing.
Mhm.
So now we know that we're going to go back. No, we don't need to do that. We'll do x equals negative pi. 1/2 x equals negative pi over 2, 1/2 x plus pi over 2 equals 0. So that's going to be our inner term there. And so the idea here, you can see if we knew this already, we can get from that r, we'd get that the period is 5. And then we'd solve for x and get that the horizontal shift is negative. So it accounts for both of those things.
Yeah.
And then last, the midline is at 1/2, so we know that we have just a plus 1/2 right there. If we wanted this to be a sine graph, we could say, oh, well, so I'll do that in a different color. If we wanted it to be a sine graph, amplitude's still going to be 2. But notice if we did it this way, we don't really have a horizontal shift, like the midline, or not the midline, like our starting point would be at x equals 0, it would just be up a little bit, right? Sine starts in the middle. Sine starts in the middle. This graph is doing the same thing. It's just up, but it's still at x equals 0. You see that? I don't know if I explained that well or not. If we look at it this way, did I successfully kind of cut that off right at the y-axis? Maybe you still see the whole window. I don't know. If you ignore the part to the left of the y-axis, you can see that this is actually hitting its midline right at x equals 0. So there's no horizontal shift. There's just a vertical shift of 1/2. So period hasn't changed, but there's no horizontal shift. And it's still just that 1/2 up. So that's just an example of how if you graph these two things, they'd be identical. It's exactly the same graph. You just kind of have to decide, or sometimes you're told, hey, look at this as a cosine graph, or hey, look at this as a sine graph. If you're looking at it as a cosine graph, then, I mean, we won't do the whole thing. You could also look at this as a cosine graph with a horizontal shift of pi, and not negative, because now if we say this is our starting point, then it starts at the top, just like a normal cosine graph. So actually, I think it'd be pretty easy to do. We could say y equals 2 cosine of 1 x minus pi over 2. Have a horizontal shift of plus pi instead of minus pi. All three of these give you exactly the same graph. You just have to decide, are you using sine or cosine? And then what's your starting point?
Okay.
Ooh, okay. That's most of it. I might throw you a thing or two later. How the formula for I'm still talking about how the formula for the argument determines the phase shift. That's the same as like a horizontal shift. And the rate at which the terminal ray rotates. We will figure out what terminal ray they're talking about. Okay, first pi. There we go. It's not oh. You've done stuff with the unit circle, right?
Yeah.
Still there?
Hello?
Yeah, you've done stuff with the unit circle, right?
Yeah, I have.
So if you think of like rotating through a unit circle
Mhm.
and getting the sine and cosine at each point as you rotate through.
Mhm.
The terminal ray is like the terminal angle. So
Yeah.
if you have like sine of 2x, you're rotating through it faster. That's what they mean by terminal ray. It's just the period essentially. So
Mhm.
okay. Definitely let me know if you have questions that come up later.
Okay.
It's complex stuff.
Yeah, I think I kind of get the gist of it.
Yeah, I think
So,
that's a good start. I'll send you the recording and I'll send you the notes in a little bit. So
okay.
all right.
Thank you.
Enjoy the rest of your weekend.
You too.